5.2, number 64. It says that Ln, a left endpoint approximation within rectangles, so an arbitrary number of them, is 1 on n sum I equals 1 to n of I minus 1 on n. And we're supposed to express this limit, right? Express the limit as n approaches infinity of Ln as a definite integral. All right, so the idea here is you got some arbitrary left endpoint approximation to something. We don't know what it is. I don't know what the function is. I don't know what the interval is. If I know the function and the interval, I can certainly write this as a definite integral. It's not a problem. So the limit as n goes to infinity is just increasing the number of rectangles. And so this left endpoint approximation to whatever it is we don't know right now, I don't have any insight into that at the moment, we'll just keep getting better and better until it becomes the exact value of the area between the curve and the x-axis. Now, let's go ahead and write this limit. Limit of this expression as n goes towards infinity is the limit of the right-hand side, of course. And it's going to start to appear more and more like the definition of a definite integral. So we just have to, some of it's visual, some of it's algebraic, kind of mixed together. And so we have this expression. I want to figure out what function were we talking about, what interval were we talking about. So first thing is, I'm going to put this 1 on n, in a sense, back inside here. I think that will help to elucidate what's going on. It can be on the outside because the summation is dealing with I changing, not n changing, so it's okay for it to exist on the outside. But I can go ahead and move it back in. The limit won't be affected by that whatsoever. Okay, so here now we're starting to get closer to the appearance of a definite integral from its definition. Put that there for 1 second, and then 1 on n. And remember the definition of integral. I'm going to leave this here for one moment. The definition of integral is a limit as n approaches infinity, Riemann sum I equals 1 to n, f of some kind of sampling, right? A sample value in here, but we know it's a left endpoint. They said it's the left endpoint. So therefore the sampling should be a plus, now I cannot write I delta x because I is starting at 1. This is a little confusing, but try to follow here. I gotta write I minus 1 delta x. Okay. If it had been a right endpoint, I would have just written I delta x because when I is 1, I'd have the starting point plus 1 delta x n, which would give me the right-hand side of the first rectangle. But since I'm dealing with the left-hand side of the first rectangle, I'm doing the left endpoint of the first rectangle, my first rectangular left endpoint should be a itself. It should be the starting point of the interval. So to cause that to happen, I've got to decrement the I value in here by 1, so that on the first move, in a sense, if you were to start to compute this, you'd plug 1 in here. 1 minus 1 is 0. I have no delta x move inward. I'm sitting on the left-hand side of the first rectangle. Okay, so for the left endpoint problem, you want to use I minus 1 in here instead of I, and on the right endpoint problem, you'll use I. And then delta x on the outside of the whole thing. Right? Again, base length of rectangle times height of rectangle, left endpoint, because when I starts at 1, delta x should be multiplied by 0, so you have not moved. You don't want to move to the right side of the first rectangle, you want to stay on the left side of the first rectangle. And then this expression will keep you on the left side, the left endpoint of each rectangle. All right, so we start to compare these two now, right? That's the idea. You want to compare these two. So a couple things start to stand out. One is certainly f of a plus I minus 1 delta x is equal to I minus 1 on n, right? This parenthesized portion here and this function expression here must be the same, and delta x is the 1 on n. Just in terms of structure, that makes sense. It could be wrong, but it's highly unlikely. Okay? So now we have these two separated off. Now we know that delta x is b minus a over n by definition, right? The two extremities of the interval we're talking about subtracted off, giving us the length of the interval divided by the number of rectangles. So it looks like b minus a has to be 1. Right? That's the implication we get from here. So b minus a equals 1. And over here, I see a plus I minus 1 delta x. Now I know delta x is 1 on n, or at least that's my supposition. We'll see if it works or not. So therefore, this is the same as saying f of something. Again, I don't know this initial point in our interval yet, which will play a role over here as well. I don't know it yet, pretext. And I want to write 1 on n for delta x now, because we're pretty confident that's what it is from the structure. 1 on n. Okay. That's inside the function there. So once I start comparing this with this, all right, a little more thoroughly, but look carefully, I see the I minus 1 on n sitting right here in front of me. I minus 1 on n, I minus 1 on n. So if this whole thing is to be I minus 1 on n, but yet it contains I minus 1 on n, just think about it for a moment. It must be that a is 0, and the function must do nothing to the input. Okay? So this implies to me, it may be totally obvious at first, it implies to me that a is 0, and the function which does nothing to its input, right? That if it receives in I minus 1 on n, it puts out I minus 1 on n. What function would do that? Well, the identity function x, it's just the function x. Okay? But if a is 0 from our analysis over here, then a is 0 here. It's the starting point of the interval we're talking about, and b must be 1. Okay? If a equals 0, then b equals 1. And now I know my interval ab, right, is nothing other than 0, 1. But I also know my function is x. Okay? Now I have the function, and I have the interval. So therefore, my integral must be integral over the interval 0, 1 of f of x, just x, dx. There is our definite integral expression for this particular limit of a left endpoint Riemann sum.